So say, for instance, you've got like a flat surface there, and you have two blocks attached to one another. It doesn't matter. This can be 3 kg, and this can be 2 kilogram. Let's say the friction on the 3 kg, you are able to work that out. If I tell you, give you a coefficient, you'll be able to work that out.
Yeah.
Okay. Did you also do a section in your book on static and kinetic friction?
We did that in the beginning.
But you do understand the difference, eh?
Yeah.
Okay, let's say the friction on the 3 kg is 6 newtons, and then the friction on the 2 kilograms should be 4 newtons. So if it's the same surface and the same type of block, the friction will be directly proportional to the mass or the weight. Okay, you won't always find that. Someone might set up a paper and will make the 2 kg friction 2 Newton or 1 Newton. It's strictly speaking wrong. If it's the same object, type of material. Okay, doesn't matter. I want to know, okay, let's do free body diagram of both. Right, let's do 3 kg block. There's a normal force. Do you use N or Fn?
N.
And then downwards, do you use Fg or W for weight?
FG.
Fg. Okay. Let's assume that someone's now pushing these two blocks with what? 25 newtons to the right. Then on the 3 kg block, there will be a force to the right. I'm just going to make it F, or you can make it FA for applied force. And then there's what? Frictional force to the back or to the left. And there's another force. There's the force that the 2 kg exerts on the 3 kg block. That 2 kilogram block is pushing the 3 kg block to the left. You've got that. It's not too difficult. So this is the 3 kg block. And then we'll also have forces, oops, on the 2 kg block. Okay, so there's a normal force. And there's a force to the right. It's the force that the 3 block exerts on the 2 block. Let's just put that in. And then there's Fg to the bottom, and there's friction to the left. Look at those free body diagrams. The 25 Newton is not exerted on the 2 kg block. The only forces on the 2 kg block is the force that the 3 kg is exerting on the 2 kg. Do you want to screenshot that or make a note of that?
Yeah, I made a note.
Okay, good. And now they're going to ask you whatever. What's acceleration? Have you done any examples like this?
I came across a few of these.
Okay. A few.
Yeah.
Huh? It's Monday morning, Mira. You should be happy and what?
No, I'm just sick. That's why I'm at home. Yeah.
What's wrong? Like a flu or something?
Yeah, flu. So I'm gonna have to go for a COVID test just to make sure.
Oh, so you're not at home today?
I'm at home today.
Right. Acceleration of the system. Now, this really, I just want to show you something that you're not allowed to do anymore. In the past, I'm going to focus on this just to show you these alternative ways of doing it. In the past, we just did the following. We are not allowed to do that anymore. We just made a drawing. We put all the blocks together in one. And we say, okay, all the forces to the right is 25 Newton. And would you agree all the forces to the left is 10 Newton? It's those two frictional forces. And then we would say FR is MA. So the resultant force is 25 minus 10. And that is a total mass of 5A. That was really easy. So 15 equals 5a. A is 3 meters per second squared to the right. Now you get 0 marks for this. You're not allowed to do this anymore. That worked for various systems. I'll show you another example now. So the CAP syllabus does not allow single system calculations. They want you to do the following. They want you to work out F net equals MA of the 3 kg and F net equals MA of the 2 kg, and then solve this simultaneously. That's quite a nice system to test your answer, isn't it? So you know the answer is 3. So now we have let's choose the direction to the right as positive. Now you have the following forces on the 3 kg. I have a applied force plus a negative friction force, and that is 3A. The applied force is 25. Oh, I've missed out a force. Look at my free body diagram. Tell me which force I missed out. I missed out writing this one, the force that the 2 kg exerts on the 3. That was two forces to the left and 1 to the right, plus a negative force 2 on 3. So now I have 25 minus 6 minus the force that the 2 kg exerts on the 3 kg, and that is 3A. Now I'm going to make the force that the 2 kg box exerts the subject of the equation. Why? I'm going to use Newton 3. Because the force that the 2 exerts on the 3 must be the same that the 3 exerts on the 2. That is Newton 3. So now I have 19 minus F2/3. And that is my first equation. Now I have to do the same. So I'm going to get some more space here. I have to do the same for the 2 kg block drawing. F net equals MA. So the force of the 3 kg on the 2 kg is positive because it's to the right. Plus your negative frictional force is the mass 2A. I'm going to make this the equation, and that equals 2A plus the frictional force of 4 Newton. Now, these two forces are the same because of Newton 3. Newton 3 says that those are pair forces that basically, those are Newton 3 forces because the one is to the one direction, other direction, but they're the same. Did you study that Newton 3 law? The definition.
Yeah.
You must just be able to read, just to rewrite that. Okay, anyway. So 19 minus F23 equals 2A plus 4. I missed out here. I also had a minus 3A. Minus 3A. Let's bring that over. So I'm going to take all. Okay, I've got something wrong here. Let me just redo this. Okay, let's start again. This force here equals that one. So this bit here would equal that. Oh, I left that F23 on the left-hand side as well. That's why it was wrong. So negative 3A plus 19 equals what? 2A plus 4. Oh, I see. Now I have 5A, and 19 minus 4 is 15. Therefore, A is 3 meters per second square to the right. Same answer. Huge difference in calculation work. There's the one sum that you must do, and there's the other one. It's a huge difference.
This one is much longer.
Yeah, unfortunately, it's the one you have to use. Let me show you another example, which from Newton 2. So there's a block. It says 10 kg. And the frictional force is 20 newtons. It's a huge force. Then I have a ball there, or a weight there. Let's say the mass is what? 8 kilograms. There's tension in the rope. Now, if you want to find out the acceleration, you have to draw free body diagrams of both of them. And you have to work out F net of both of them and solve it simultaneously. In the previous system, which we're going to use just as a test method, we're going to just put both these together as one unit and make it 18 kg. And then all the forces to the left is 20 newtons, because that's the only frictional force to the left. All the forces to the right is the force that the 8 kg exerts on the rope because of its weight. So in other words, if you just leave it, if it's not moving, then there's a potential 20 Newton to the left, and there's potential of 8 times 9,8 to the right. So F net equals MA. The net force is the FG component minus the friction, and that's the mass of 80A. So that's 8 times 9,8 minus 20 equals 18A. And that's the answer. That was the sum. That we did it for years like that. And then they, I don't know, they wanted to be clever. So the answer is 3,24 meters per second square. But now you have to treat both of these weights as different entities and solve it simultaneously. There's a reason. And the reason is that the movement of these two units are not linear. So you can't treat it really as a single fixed system. But that doesn't make sense because the answer is exactly the same. Anyway, you're not allowed to do this. You have to set up equations for both of them.
Okay.
All right. I need to send you something to do. I need to send you some work, but I have sent you some stuff.
Yeah,
I
on
sent you
that
some stuff
login.
on Newton 1 and 2, but it was it Afrikaans? No. Did you get a login for the science part, or only a login for maths?
No, I have the science one as well.
Yeah, the science one. Okay, you must somehow go and test that program.
I'll do that today.
Yeah, well, and then I have to translate some of all the tests are in Afrikaans. So somehow I have to find time to translate it.
Okay.
But at the moment, you still have examples in your textbook that you can do.
Yeah.
Okay, let me do that. Okay, what's the next section of the work? Because I'm not going to teach you any of this if you know it already, or if you're fine with it, then we're going to waste time.
Yeah,
So we've done Newton's laws. This was quite quick, eh? You know, if you were in a normal school, you would have just finished vectors now, started with Newton.
Yeah.
The next one is Newton's law of universal gravitation.
Yeah, that's the next section.
That's the next one. Let's talk about that. Okay, so Newton said the following. Let's just write that. Okay, let's just make a little heading here. Okay, so Newton said any object in the universe, because of the fact that it has mass, will attract any other object. So there's an object, let's say it's a planet or a star or moon or whatever. And that object will attract any other object. So there's a force of attraction between those two objects. And those forces are directly proportional to the product of the two masses. In other words, the bigger these two objects' mass, like the Earth has got a 6 million ton mass. 6 times 10 to the power of 24 or something. That's much more than 6 ton or 6 million ton. So the bigger the object, the higher the force. The force is also inversely proportional to the distance squared between the objects. So the closer they get to one another, the higher the force. But that sounds kind of logic. Just think about two magnets. The closer you bring the magnets to one another, the stronger the force. The bigger or the stronger the magnets are, the stronger the force. Okay, does that make sense?
Yeah.
So you get like a sun. In our little solar system, the sun is the biggest object. So the sun is in the middle of our solar system and attracts all the other planets. And that's why they move around the sun. The other planets also attract the sun, but the sun is too heavy to be moved. So you knew that in the past, people thought that the Earth was the middle of our solar system. Do you know that?
No.
You didn't know
No.
that? Well, everyone believes that. About 400 years ago, everyone believed that the Earth was in the center of our solar system and the sun moved around the Earth. Because if you look at this, have you looked at the sun? And
Yeah.
they look kind of small, eh? Huh?
But then again, people also believe the Earth was flat.
Yes. So there are some people that still do believe that. Anyway, okay. So now there's a formula. The formula looks like this. The force equals G, big G, that's universal gravitational, that's universal gravitational constant. And that is 6,67 times 10 to the power of minus 11. That's a constant. And they give it to you. Okay.
Okay.
And then m1 times m2 over r squared. So in other words, I can determine the force between those two objects by taking the universal gravitational force, constant rather, not a force, and then I multiplied it with m1. Let's say m1 is sun and m2 is the earth. And then I divide it with the distance between them in meters square. So the mass is in kilograms. G is a unit they give you. It's a constant. And they give that value to you. And then R is in meters. Very important if you've got to write units, because we're going to talk about large distances maybe and big masses. So it's not very difficult. Also very important, R is the distance between the centers. So R is the distance between the center of the moon or the earth and the center of the moon. So that's R. Not the surface. Remember, the earth has a big radius. So there's actually a huge difference between the distance from its center to the center and from its surface to some other center. Okay, this is not difficult. The basic stuff is not difficult. So now I've got the earth here. Okay. Earth has a mass. Okay, let's say earth. The mass equals 5,98 times 10 to the power of, I think it's 24. You get that on a little sheet as well, formula sheet. Let's say there's a satellite here. And it has a mass of 5,000 kilograms. Let's say 15,000. 5,000 is like a small. 15,000 kilogram satellite. Now, let's say the radius of the Earth is, I think it's 3,8 or something. No, it's 6,38. You should get that on your formula sheet. You can't know this. Okay, I just want to get a better eraser. 6,38 times 10 to the power of 6 meters. Okay. Now, let's assume, I'm going to try and make this difficult. Let's assume the distance from the Earth's surface is what? 5,000 kilometers. It's 5,000 kilometers from the distance of the surface of the Earth to the satellite. I want to know, what is the force that the Earth exerts on the satellite? Okay, I'm going to show you the sum. It's not difficult. Just a couple of things you have to take in mind. You have to write down the formula, and therefore you have to have the formula. Now, okay, so I want the force. The G bit is 6,67 times 10 to the power of minus 11. That they give you. So they give you this formula, and they give you that G value. And then the mass of the Earth is 5,98 times 10 to the power of 24 times M2, which is the mass of the satellite, and that's just 15,000. The satellite is too small to worry about the radius. Okay, if they don't give you a radius of an object like a stone or a satellite or what, then the radius is not applicable. The radius might be like 100 meters, and we compare it to 5,000 kilometers. Do you understand?
Yeah.
Okay, now the distance between the center of the Earth and the satellite is the distance from the surface to the satellite plus the radius. Do you agree?
Yeah.
So you have to have that total distance. They've just given me the distance from the surface of the Earth to the satellite, not the radius. Not the center of the Earth. So I have to add the radius. So it's 6,38 times 10 to the power of 6 plus 5,000 times another 1,000, because the distance is in meters. Okay. You with me?
Yeah.
Squared. Good. There we go. Now, most students don't do well in this section simply because they don't know how to use a calculator. They make some error in typing. I have I have 150,000 in the equation. That's wrong. It's only 15,000. Okay. See that?
Okay.
Sure. I guess it's not 46199. You get that? 46199,91 13.
Yeah.
Okay, what's that? That's the force. That's the force that the Earth attracts the satellite, and the satellite attracts the Earth. Remember, the Earth is attracting the satellite, but the satellite is also attracting the Earth with the same force, Newton 3. So the satellite is moving around the Earth. The Earth is not moving around the satellite. The simple reason is that the satellite's weight is much less, and the satellite can actually move at that force. If you exert a force of 4,600 and, well, no, it's 46, isn't it?
Mm-hmm.
46,000 newtons on the Earth, it's not going to move. Why? It's too heavy. Its mass is too big. So that's a small force. The Earth is not going to move, but the satellite's going to move. Okay, this is one section of the work that you need to be able to understand and do. They are also going to test you in short questions in this chapter. So they're going to have two objects. Let's say A and B. Let's see if we can figure this out. Now, the distance between A and B is R, and the force of attraction is F. So there's a force of F between A and B when they are apart. It's basic. So when the distance between them is R, there's a specific force F, and let's say the mass is equal. The mass of A and B is equal. So it's the mass is just M. Okay. Now what I'm going to do, I'm going to double the mass of A. What will the force be? Let's say A, the force will be F. B, the force will be 2F. C, the force will be 4F. And D, the force would be half F. Okay, now they're going to ask you which one is correct. You have to figure out which one of those are correct.
Is it not B?
Yeah. Yeah, it's B. I mean, this work is not difficult. You're just brand new to you, so that's why you're worrying. Okay, I'll show you how to do it. This equation, G M over R squared. Okay, let's say initially, that's the equation. That's what it was at the beginning, before we doubled something. Now we're just going to do the following. I'm just going to say the one mass doubles, so it's 2M now, times M over R squared. So I'm going to take the 2 and put it in front. So that's 2GMM over R squared. So that 2 just jumped in front. You understand the math there?
Yeah.
So that section there is the same. That's F. So the answer is 2F. Now that method in red I showed you is quite helpful when it becomes more involved. So in number 2, I'm going to ask you if the distance doubles. In other words, I take them and I put them double distance apart. I move them double R apart, or 2R away from one another. What would the force then be? Will it be A, F, B, 2F, C, half F, or D, quarter F?
Is it not 2F?
Okay, let's see. Let's just find logic first. If we take them further away from one another, the force should be less. The closer they get to one another, think of magnets. The closer you bring the magnets towards one another, the stronger the force. The further you draw them away from one another, the weaker the force. That sounds logic. So my logic tells me that it can't be A or B, because A and B is the same or higher. It can't be higher or the same. It must be less because I've actually taken them further away. So there's the first equation, and now I'm going to make the change. The force, the mass stays the same. So it's G, the mass of the one is the same, the mass of the other one is the same. The distance is now 2R double squared. And that becomes G M over 4R squared. If I take that 4, put it to the front, that's a quarter. Is that correct?
Oh, okay.
So the answer is a quarter. So now I'm going to test you and see if you can actually manipulate that formula and try and get on. If you get the following right, then you have, it's awesome, you can do it. Okay, so we're going to double both masses, A and B. and bring them, let's see, and double distance. We're going to bring, we're going to make double both the masses of the two objects, and we're going to double the distance. See what is the right answer. I'm not going to give you options. I just want you to work it out.
Won't we say F equals to G,
Okay.
2M?
2M times 2M now over
If you're doing both, then it want to be 2R squared.
2R squared. That's the distance between them is doubled. The mass is also doubled. So I've got a 4 on top. Is that correct?
Yeah.
And I've got a 4R squared at the bottom. And that will just cancel one another. So it remains the same.
Yeah.
The double the masses and double the distance, it's going to be the same. The force is just going to be in F. Okay. Is this difficult? Just new.
Yeah. Just needs practice.
Yeah, you need to practice this. Okay, I'll show you the last part of this. This is a very small chapter, and it will be one question in your paper. So let's assume that I'm throwing a ball, or let's assume there's the Earth. And there's an object coming towards the Earth. Now, if there's no external forces, if it's in free fall, then the gravitational acceleration will be 9.8 meters per second square. Sorry, that's to the power of 2. Do you know this?
Yeah.
Okay. So let's ask the following question. If this is 2 kilograms, and I've got another object coming towards the Earth that is 8 kg, we need to be able to prove that the acceleration will be the same, irrelevant of the mass. So the force is G. So the Earth, and let's say A and B, the Earth attracts A in a certain way and B in a certain way, so that the acceleration of both of them are the same. So that's G times mass A, mass of the Earth, mass of the object. Let's say this object is A, divided by R squared. So I'm going to work out G now. F is mg, and that is gravitational acceleration, the mass of the Earth, the mass of the object, A. But this is also the mass of the object. F mg is also the mass of the object. So I can cancel this one and that one. So the mass of the object is not applicable. I don't know if you've seen that experiment. So G, acceleration 9.8, is only directly proportional to the mass of the Earth and the radius of the Earth, not the mass of an object. If you make a vacuum, if we make a glass cylinder there, and there's a vacuum, so there's no air friction. You take a brick and a feather. Have you seen this experiment?
Mm-mm.
And you let them fall. They'll fall to the ground exactly the same time. They'll hit the ground exactly the same time. The feather and the brick will accelerate at 9.8 meters per second and hit the floor exactly at the same time. In real life, it doesn't work like that because we have, we have air resistance.
Yeah. The brick will land fast.
Pardon?
I say the brick will land fast if you have to
And
take
a
it
simple
over.
reason for that is that the brick has more momentum, so it actually overcomes the air molecules that's opposing it much easier than the feather. But if there's no molecules to overcome, then both of them will fall at the same time. Okay, but anyway, this is kind of helpful. Because this G value, if you now put in 6,67 times 10 to the power of minus 11, and you put in the mass of the Earth, which is 5,98 times 10 to the power of 24, and you divide that with the radius of the Earth, which is 6,38 times 10 to the power of 6, then you get, well, this is rounded off numbers, you'll get 9,8 roughly. So this value is true for the Earth, and only if you're on the surface of the Earth. So strictly speaking, if you go up very high on a mountain and you jump down, you won't be attracted by, or you won't accelerate by 9,8 meters per second squared, slightly less, because your distance between yourself and the radius of the Earth is slightly more. Okay, anyway, that's technical. What we can do now is find the G value of other bodies, like the moon. So say, for instance, we go to the moon. I'm just going to write that formula. F is G. Remember, this is universal. This is true for every subject, every planet, every object. So if it's the moon, I don't know the weight, but let's say it's 7,2 times 10 to the power of 23 kilograms. That's less than the Earth. I think it's much less. Do we know the weight of the moon? So let's just properly Google that.
Okay.
The weight of the moon is 7,3. I'm not really far out, actually. It's 7,346 times 10 to the power of 22 kilograms. 100 times less than the Earth. And the radius of the moon, that would be much less. No, is it? The radius of the moon is 1,736,000 meters. Okay, so we can work out the gravitation of the moon by putting those factors in. Okay, so they can say, okay, the force is G M over R squared. The force is mg, that equals to 6,67. 6,67 times 10 to the power of minus 11. The mass of the moon is 7,346 times 10 to the power of 22 times the mass of the person jumping on the moon, which is irrelevant because those two masses will cancel. And then we divide that with 1,736,000 squared. Okay, let's type that in a calculator. This is one way of doing it. So it's just 6.67 times 10 to the power of negative 11. That's wrong. 1,63. You get that?
Yeah, 1,60.
I would not say it's that low. Okay, fine, fair enough. Okay, so this is straightforward, but you won't get something like this. This is too straightforward. They're going to do the following. We're almost finished. They're going to do the following. They're going to say, there's a planet. It's X. We don't know what it is. Its radius is what? 2/3 of that of the Earth. Come. That of Earth. It has a mass of half of Earth. what is his gravitational acceleration? Okay, now we're going to do the following. Now, this is very important to be able to do something like this. I'm going to start here with the Earth. I'm going to tackle it the same way I did that first sum. I'm going to say that this calculation, this F equals G mm over R square is true of every mass, every object, every planet, every sun, every star, whatever. And I'm going to do this. F equals mg, and that is G times the mass of the Earth times the mass of the object falling to the Earth divided by R squared. These two masses will cancel one another. So G, the G-force, or the G-force, the gravitational acceleration is G times m over R squared. And that's 9.8 on Earth. So now I'm going to go to this planet X. And I'm going to say this formula also is exactly the same for that planet. It's universal. And F is also mg. So that mass of that planet is 2/3 of m, the mass of the Earth. So m becomes the mass of the Earth. And that planet is a 2/3 mass. And this object falling to that planet is irrelevant because I'm going to cancel it. And the radius is half the radius of the Earth squared. So now I have G equals big G. And then I'm going to do 2/3 over a half square is a quarter. And that becomes 8/3, isn't it?
Yeah.
So that becomes 8/3 with G and an M on top and an R square at the bottom. I've taken out all those values and put it in front. So now look at this. G times M over R square is 9.8. So the gravitational acceleration of that planet is 8/3 times 9.8. Because 9.8 is this. And then I just put that in my calculator. That's 26.13. And that is meters per second square. Okay, this is what I want to do today in this chapter. You first need to go and look at that chapter. But before we finish, I'm just going to stop the recording. Before we